So in this video, we're going to talk about tangents and areas with parametrized curves. So first of all, let's say that I've got a curve x equals f of t and y equals g of t. So this describes some parametrized curve. So the curve is differentiable as long as f and g are both differentiable at t. So how do we get to the derivatives for x and y? Well, we do have a formula for this. So the parametric formula for dy dx is just going to be you take dy dt, so you take the derivative of y with respect to t, and then divide that by dx dt, so that's the derivative of x with respect to t. So this is, I think, actually like a pretty straightforward formula. You have dy dx, it's just dy over dx. Okay, cool. Now, the slightly more tricky formula is when we want to take the second derivative, and this will probably be best understood with an example. So provided that the derivatives exist, the second derivative is described as dy prime over dt over dx dt. So this y prime is my first derivative. So basically what this is getting at is that you take the derivative of the first derivative and then divide that by dx dt. So this is a little bit more complicated, and like I said, I think it's best understood with an example, so we'll just kind of jump right into it. Okay, so first, let's just use the derivative formula. So the question here is to find the tangent to the curve at the given value of t. So I have this curve, x equals 2 sine 2 pi t, and y equals cosine 2 pi t, and then t equals negative 1 over 6. So it may have been a minute since you've done derivatives, but the word tangent really goes hand in hand with the idea of taking a derivative. So the first thing that we've got to do is we must find the slope at the point. And so to find the slope at the point, that means that we need to take the derivative. So if you completely forgot derivatives, things to remember: tangent, slope at the point, and derivative, they all go hand in hand. So you might want to write down just some extra instructions for yourself if it's been a minute since you took any derivatives. Okay, so we're going to use our handy dandy little formula here, dy dx. This is dy dt over dx dt. So this part is straightforward. So we just have to use the chain rule here. So I take the derivative of the outside function. So for dy dt, I take the derivative of the outside, which will be negative sine. You leave the inside intact, and then you multiply that by the derivative of the inside. And then we divide by dx dt, so I take the derivative of the outside function, the derivative of sine is cosine, and then I multiply by the derivative of the inside function. Now, I will say, if it's been a minute since you've done any derivatives, I do have a summary video just reviewing all the derivative rules. It might be worth it for you to go back and review some of these, especially using the chain rule, because you're going to probably use that a lot when you're talking about taking derivatives of parametrized curves. So just a heads up on that. Okay, so anyways, so I've got all this, and so as you can see, I can make some simplifications and cross out my 2 pi's. So my dy dx is going to be this negative sine 2 pi t over 2 cosine 2 pi t. Okay, so this is the formula for the derivative, and the concept of the derivative, this goes hand in hand with the idea of a slope at a point. So if I want to find now the slope at the point, what I'm going to do is I'm going to plug in t equals negative 1 over 6. So I'm trying to get to a tangent, which is a tangent line. So first I have to figure out what the slope is. So to figure out that slope, I plug t equals negative 1 over 6 into my derivative. So that's going to give me negative sine of negative pi over 3 over 2 cosine of negative pi over 3. So if I just evaluate all of that, that's going to give me negative square root of 3 over 2 times the square root of 1/2. And so when all is said and done, this will simplify to just square root of 3 over 2. Okay, so one more time, just to review everything in case it's been a minute. You find the derivative, you plug in the point, and when you plug in the point, that gives you your slope for the tangent line, okay? So for any line, I need a slope and I need to know a point. And all I have to go on right now is I have this t. So the next thing that I've got to do is I've got to find what is my xy coordinate using my t equals negative 1 over 6. So remember, my original equations were x equals 2 sine 2 pi t and y equals cosine 2 pi t. So from here, I plug in my negative pi over 6. So these are the two values that I need to get. So I get that my x is going to equal negative square root of 3 and my y is going to equal 1/2. Okay, cool. And so now what that means is I have a point and I have a slope. So when you have a point and a slope, those are the two things that you need to define any line. And so this will be how I figure out what my tangent is, or my tangent line. So from here, I can just use point slope form. Y minus y1 equals m times x minus x1. So I can just plug all this information in. So I plug in my point into my y1 and my x1, so I got y minus 1/2. I plug in my slope m, so that's square root of 3 over 2, and then I've got x plus square root of 3. And from here, I can just multiply everything out to get my tangent line. So I distribute everything, and when I'm done collecting my like terms and all that good stuff, this is going to come out to square root of 3 plus 2, and that's my tangent line. So that's everything that goes into finding a tangent line. So now what I want to do is I want to talk about how do we find the second derivative. And we're going to find the second derivative of the same situation. Okay, so remember, for the second derivative, this formula now is this dy prime dt over dx dt. So what we're going to have to do is we're going to have to first remember, so y prime is my original first derivative. So that's where I've got to start. So just as a reminder, before what we found was my derivative was negative sine 2 pi t over 2 cosine 2 pi t. Okay, so now to figure out what is my dy prime dt, well, basically dy prime dt, that is taking the derivative of the first derivative. So I take the derivative of this whole thing here. So again, this is a plug for if you forgot your derivatives. I do have like a crash course summary video going through all of these rules, because now you got to bust out the old quotient rule. Quotient rule is you take the derivative of the top function times the bottom function minus the top function times the derivative of the bottom function, all of that divided by the bottom function squared. So if you're rusty on these, you might have to go back and review, because this is typically a prerequisite for a calculus, like a calculus class at this level, and so you would just be expected to bust these out. Okay, so I actually think this is a great moment for you just to test what you remember about derivatives and just see, like, you're gonna have to use the chain rule and you're gonna have to use this rule. So what I want to recommend is that you now take a moment to find the derivative of this. You are going to have to use the chain rule again. So you can pause here, hit play when you're ready. Okay, so here's the structure. So I take the derivative of my top function, so this is my f here. So I take the derivative of the top function. So the derivative of sine is cosine, and then the inside function is 2 pi t, so the derivative of the inside function is 2 pi. And then I multiply all of that times the derivative of the bottom function, or sorry, not the derivative, just the bottom function, 2 cosine 2 pi t. Okay, now I subtract this and I leave the top function alone, so I leave negative sine 2 pi t alone, and I multiply this by the derivative of the bottom function. So the derivative of 2 cosine is going to be negative 2 sine. I leave the inside function intact, and then I multiply that by the derivative of the inside function, so that'll just be 2 pi. And then all of this is divided by the bottom squared. So now we have some simplifying to do, and again, I would suggest that maybe you pause here and try to simplify this as far as possible on your own before I show you. Hit play when you're ready. Okay, so I collect my like terms, so I notice here this 2 and this 2 multiply together, and I do have this minus sign, so this comes to negative 4 pi cosine squared 2 pi t, and then I've got a negative, a negative, and a negative, so this all stays negative. And I've got this 2 and this other 2 pi, so this is minus 4 pi sine squared 2 pi t. All of this divided by 2 cosine 2 pi t squared. And now, since I see a cosine squared and a sine squared, this is screaming for us to use the Pythagorean identity. So now that I'm here, I'm going to factor out the negative 4 pi, and notice what I'm left with. Cosine squared 2 pi t plus sine squared 2 pi t. And so this part here, now this just equals 1. So I am just left with on top negative 4 pi, and then I can square the bottom. So this bottom now, this is going to be 2 squared is 4, and then this is cosine squared 2 pi t. So now I can cancel out my 4's, and I'm just left with negative pi over cosine squared 2 pi t. So I could write this like this, or I could write this as negative pi secant squared 2 pi t. Okay, now remember, that was only the first part. So this was the formula, right? It was d squared y over dx squared. So now I've got my dy prime over dt, and I need to still derive that, or divide that by dx dt. Well, the good news is that now I have the top part. We figured out the top part, right? And I do know dx dt that I can recycle from an earlier problem. So here's what I've got. And so I know that secant squared is going to be equal to cosine squared. I just have to send it to the bottom. So I can resimplify this to negative pi over 2 cosine cubed 2 pi t. And so then we were supposed to evaluate this at t equals negative 1/6. So now I can plug in negative 1/6 into this. So effectively I have negative pi over 2 cosine cubed negative pi over 3. So if I plug all of that in, I get negative pi over 2 times 1/2 cubed. And so that's going to turn into negative pi over 1/4. And so ultimately I just get negative 4 pi as my final answer here. Okay, so that might take a little bit of time. So now let's do a similar question. However, let's change it up a little bit. So now I want to find the slope of the curve at the given t. So I'm going to have x equals t cubed plus t. And then my second equation is y plus 2t cubed equals tx plus t squared. And I want to evaluate this at t equals 1. Okay, so in this case, what we have here are we have the need to use implicit differentiation. So again, if you have totally forgotten your derivatives, 1-hour crash course video, strongly recommend you go check it out. Okay, so I need to find the slope and to figure out the slope at a point. So ultimately, once again, I'm still trying to do my dy dx. So I'm still just going to use this formula here. It's just in this case, this is just slightly more complicated because I have now all these other variables kind of running amok, but that's okay. We'll get through it. So let's start with the easy one. So let's start with dx dt. So for my dx dt, I can just take the derivative of this. So this is just 3t cubed plus 1, or sorry, 3t squared, 3t squared. Cool. All right, great. We're halfway done. So now let's work on this second equation. So with implicit differentiation, so what I'm going to do in this case is each time I take a derivative of x or of y, I'm just going to write dy dt or dx dt when I take the derivative of x or y. So I'll show you in a second. So let's just go ahead and do it. So I've got this derivative here. Okay, so the derivative of y is 1. So I've got 1, but then I'm going to write dy dt. And so that tells me then that I took the derivative of y, but I'm now keeping it with respect to t. Now, the next one I can just go ahead and take the derivative of, so 2t cubed. So the derivative of that is going to be 6t squared. Since I'm taking the derivative, everything is with respect to t, I don't have to write anything next to it. So that one is just assumed. Next, I have this 2x. So the derivative of 2x is 2, but since now I'm taking everything with respect to t, I'm going to write dx dt. And then finally, this is going to be plus 2t. Okay, so ultimately, what I need is I need to solve for this. But before I can solve for this, I also need to resolve the fact that I have this dx dt here. And so this result I can plug into my dx dt. Okay, so we have a little bit of work to do. So let's see, let me clear some space. So I'm going to rewrite this as dy dt plus 6t squared plus 2, 3t squared plus 1 plus 2t. Okay, cool. And now I have something that's entirely in terms of t that I can easily solve for dy dt. So let's just make a little space. And, oops, I think I lost my equal sign in the previous step. Sorry, there was an equal sign here. There is an equal sign here. Cool. Okay, so now I'm going to have dy dt. This is going to equal 6t squared plus 2 plus 2t. And now I'm going to subtract off this 6t squared minus 6t squared. So ultimately, I'm left with my dy dt. It looks like these 6t squareds drop out, so I'm just left with 2 plus 2t. Cool. And so now I can write my dy dx. So remember, this is ultimately dy dt over dx dt. And now I have both of these pieces. So this is 2 plus 2t, and this is 3t plus 1. And so ultimately, I was supposed to find the slope. Let's see, what was it? The slope at t equals 1. So if I want to find the slope at a point, so now I just need to plug in the t. So if I plug in t equals 1, let's see, I'll just do that here. So this becomes 2 plus 2 over 3 plus 1. So that's going to be 4 over 4. So ultimately, this is just going to equal 1. So that's going to be our slope in this case. Okay, so that's our implicit differentiation. And now let's go the other direction. So let's talk about finding the area enclosed by the y-axis and the curve x equals t minus t squared and y equals 1 plus e to the negative t. All right, so I am not going to lie to you. This one's actually going to be a pretty challenging one. So first of all, you have to understand, so we're talking about area. So area is talking about integrals. But we are actually going to use the knowledge that we've just talked about to help us set up the integral, plus also stuff that we've known about integrals in the past. So in general, to figure out anything with area, the first thing that you've really got to know is it would be best to know what this picture actually looks like. So you can Google, like in this case, I think like this is going to be something that's kind of hard to graph. So this is something where I think you would need like a reference really to do this in a timed situation, because this would take you a while to graph. So if you can't easily figure out the graph, I think it's kind of one of those cases where it would be okay to use a grapher just to get a reference. And I can't imagine how you could do this without having a grapher. So anyways, you can look up just like parametric equation grapher. Desmos does have one. So let's just take a look at the graph real quick. Okay, so like I said, you can just Google this, so parametric graphing on Desmos, and you just put in the form of your x and your y. So you can see I just plugged it all in here, and I just gave myself like a really generous range for t. So this graph, like I said, I don't think this graph would be easy to figure out, right? Like you kind of need some sort of reference for it, really. So if I zoom in on it, so it's supposed to be between the y-axis and the graph. So we're talking about just this little shape in here. And so if you think about the good old days of using integrals to figure out area, so in this case, you want to choose what's going to be easiest to like kind of set up the area with. And just looking at this, I think it's going to be difficult to figure out what is this last point here on the x-axis. So this clearly starts at x equals 0, but like you're going to have to do probably a lot of work to figure out where is this kind of peak point, right? Because I don't know what the graph of this is in just a Cartesian equation. Like this is a hard Cartesian equation to just figure out. And so it's kind of hard to figure out what is this exact point right here. So the easier way to go with this is to actually graph using these 2 points here, which means that I'm thinking about my area going from bottom to top, which means that I am integrating technically with respect to y. So typically when we are using integrals for area, we integrate with respect to what's ever easiest to figure out, and sometimes that just comes down to the bounds. So I could probably easily figure out what this bound is and this bound is. Now, we also have to think about this in terms of parametric equations, right? So when I'm looking at these 2 points, I'm looking at where the x coordinates are equal to 0, okay? So this is all going to kind of mess with you a little bit, so you really want to have a good picture in mind before you get going with this. Okay, so let's set up the general idea of the integral now. Okay, so our game plan, just our general game plan, is that we're going to follow whatever the x curve is tracing out, and we are using the coordinates on the y-axis, so we're integrating everything with respect to y. So what I'm saying is that if this were a normal Cartesian equation, this would be the setup here. Now, we have quite a bit more work to do because now we need to convert everything to this parametrized curve. So to convert everything to parametrization, well, the x part I have, right? So that's this part of the curve right here. So I can convert this part to t pretty easily. And then for the dy, so now I just have to think about what I know about dy. So dy dt, I can rewrite dy as dy dt times dt. So we can view the differentiation like this. This will be equivalent to my dy, but then basically what this is telling me, right, is to take the derivative of y with respect to t. So I need to take the derivative of this. Okay, so let's go ahead and do that. So my dy dt I know will be negative e to the negative t. And then I need to figure out where x equals 0. So remember, x equals 0 is where that curve crosses the y-axis. And so that's going to help us figure out our limits of integration here. Okay, so what I'm going to do is I've got my x equals t minus t squared. I want to figure out where does this equal 0. That's where this is going to cross the y-axis. So I can figure this part out. This is just, your standard algebra equation, so I can factor a t out. So this will equal 0 when t equals 0 and 1. Now, this is not the whole story. I need to think about when t equals 0 and 1, what is the value of the y's for each one of these? So when t equals 0, if I plug that into the parameterization for my y, I get 1 plus e to the 0. Oops, and this should be 2. Sorry, this should be 2, not 1. So this becomes 1 plus anything to the 0 powers 1. So this is 1 plus 1, so this equals 2. And then when t equals 1, so if I plug that in, I have 1 plus 1 over e. And okay, so now if I think about these two values, which is higher? 2 is bigger than 1 plus 1 over e. So when I'm setting up my limits of integration, I want to put everything in terms of t now, but I'm using these like y's to kind of guide this. So this is where my highest value is at t equals 0, and my lowest value is at t equals 1. So here is how I set up my limits of integration, because at t equals 0, this is where my highest y value is. At t equals 1, this is where my lowest y value is. Okay, and so now we can go ahead and integrate this. And how do we integrate this? Like I said, this one has kind of got some meat to it. We're going to need to use integration by parts. So I'm going to set my u equal to t minus t squared, and that means that my du will be 1 minus 2t dt. And then my dv will be equal negative e to the negative t dt, which makes my v e to the negative t. And so let's drop the limits of integration for a moment. So my uv, so this will be t minus t squared e to the negative t, minus my v du, so this will be 1 minus 2t e to the negative t dt. Okay, so there's everything. And now I need to integrate by parts again. So start it over. My u will be 1 minus 2t. My du will be negative 2 dt. My dv will be e to the negative t, and my v will be negative e to the negative t. Oops, and I forgot my dt. Okay, so wash, rinse, repeat. So let's make some space. Okay, so I've got t minus t squared e to the negative t. Let's be careful with this. I'm going to set up a nice big set of brackets. So I've got my uv, so this is 1 minus, this should be negative 1 minus 2t e to the negative t. So there's my uv, minus my v du. So I've got a negative and a negative, so those both cancel out, so I can just keep that negative here. So this will be minus 2 e to the negative t dt. Okay, so there's everything. So this is going to be t minus t squared e to the negative t plus 1 minus t squared e to the negative t. And then, let's see, this minus here will cancel out with this one, but then I still have this minus. So just be careful with all these minus signs. This becomes minus e to the negative t. Okay, and now I need to evaluate all of this for my limits of integration. So remember, these limits of integration went from 1 to 0. Okay, so now let's go ahead and start plugging things in. So plugging 0 into this is just going to leave me 0. And then here, this is going to be 1 times e to the 0 will just be 1. And then minus 2 times e to the 0, so this will be minus 2. Okay. And then I need to subtract off. So this will give me, so if I plug in my 1, I have 1 minus 1, so this is going to be a 0. This will be 1 minus 2 e to the negative 1. And then this will be minus 2 e to the negative 1. So let's see. So then I'm left with negative 1 minus negative 1 over e minus 2 over e. And so it looks like I'm left with 3 over e minus 1. Okay, good times. So those are pretty challenging problems, so I'm going to leave it at that. I will drop a link in the description of the video to the summary on derivatives if that would be helpful to you. Otherwise, I'll leave it at that, and I'll catch you guys in another video. Bye!